Oh, what else is on there?
At 11 o'clock was restoring boat anchors. And 12 o'clock was the ARL forum.
Okay. Thank you for showing up.
On the website.
Nice day to be outside, but you're inside. Yeah, we appreciate that. I'm Bob, W1IS.
Bob, KC1DSQ.
We're sometimes called the two Bobs. Bob and I are in our second incarnation of cooperating on technical stuff. We both worked at Digital Equipment Corporation in ancient times, and we're involved with the first I/O subsystem that used serial lines versus parallel lines for I/O devices. And we created our own protocol, and it's now called USB. And that was back in the 60s, so it's a few years ago. Anyway, we're going to talk about multi-band wire antennas and phase dipole wire beams. I'm going to take our goals from.
Okay, so a lot of transceivers have like built-in tuners that can handle about 3 to 1. So the idea is to build antennas where the SWR on all our bands is 3 to 1 or less everywhere. So we covered dipoles, off-center fed dipoles, end feds, and so one of the things we discovered doing off-center feds is that the harmonics that antenna exhibit are not integer multiples of the fundamental. They're a little bit higher. So we'll explain why that is. And we'll talk about a 40-meter dipole operating on 15 meters. That doesn't work quite as well as you would hope, and we'll show how to fix that. And so I guess we're ready for the next slide.
Okay, here's a description of what happens. If you look at an 80 meter as the lowest frequency of the band, they're harmonically related. Great, multiply by 2 or 4 or 6 or 8 or whatever it is, and it comes right up. But who operates at the bottom of the band? I don't. We operate in the middle of the band, at least somewhere around there. So if you put it in the middle of the band at 3.75 on 80 meters, and you multiply that by 2, you're up to 7.5 megahertz. So all of a sudden, if you try to work that antenna at 40 meters, it's going to be resonant way above the band. And it gets worse as time goes on. So the fact of the matter is that the lowest frequency is the one that's the hardest, because if you look at the differences in the higher bands, they're not so bad. But the 80 meter band or the 160 is always a pain in the neck. And that's why NFEDs that are built, you build it for 80 meters, you cut it for 3.6 megahertz, it might work on 40 meters, and the rest of the times it doesn't work at all. And so we've got that problem solved. We're going to tell you how to do it for yourself. It's not hard. Okay, I'll talk about this one. The second culprit that you have, other than the fact that the harmonics are not related integerally, is end effect. Now, well, that end effect is the electrical lengthening of the antenna by coupling it to ground. Typically, ground is the place where you couple it. And so the closer you put an antenna to ground, the antenna is going to feel like it's longer. So if you ever tune an antenna, let's say you put up a 20-meter dipole, you tune it at 5 feet off the ground, you put it, and it's looking great. You put it up 30 feet, and all of a sudden, the SWR is not right. And that's the reason. End effect is becoming less as you go up in the air. So what is end effect? It's coupling basically of the ends of the antenna to the ground and other objects. And that makes, when you have energy coming off the end of the antenna, coupled to something else that says, wait a minute, the end of the antenna, which its current should stop at the end, it doesn't. It keeps flowing to other places. That makes the antenna look longer. That's what end effect is.
So the order of magnitude for that, we use 468 over F to determine the length of the dipole, and that takes into account this end effect. If you calculate with the speed of light in free space, it would be 492 over F. So that's the percentage difference we're looking at here.
So if you look at an antenna, let's just take a 40-meter antenna. I think I have it here in the next slide. Okay, that's a 40-meter antenna operating on 15 meters. Each of those humps is a 15-meter voltage distribution. So if you look at it right now, there's end effect on the ends, but there's no end effect in the middle. And so now if you let's take that up to 10 meters, and we have all these humps going along, and there's only end effect over here. So as a result, the antenna is going to look longer than you think. And you've got to figure out how to fix that. So if you tune it for 10 meters, then it's going to be screwed up on 80 meters. And that's basically the way it works. Go ahead, Bob.
Okay. So that's the reason the resonances are not integer multiples of the fundamental, which blew my mind when I first figured it out. So it is the formula we came up with for calculating the length to cut an antenna to resonate on a certain harmonic is 470, 468, or 470 times 1 minus the number of harmonics minus 1 plus 492 over f. So you've got
one antenna. You got one antenna that has end effect, which are the two N1s, and you got two antennas with no end effect. Therefore, it's N minus 1. Now, if you look up the formula in the handbook, it's wrong. This is the right formula. Okay, I think that's it. Okay, here it is.
Okay,
this is the reality.
Okay, so we cut the length of the dipole for 15 meters because we know how to fix it for 40. So, okay, the basic problem is if we do cut it for 40 meters, then the resonance for 15 will be 22.1 megahertz. Whereas if we cut it for 15 meters, then that resonance will be right, but the 40 meter will be below the bottom of the band, 6.86 megahertz. So what we do is we cut the antenna for 15 meters and we'll fix 40.
So the question is, what do two poor boys west of Boston do? Aha. The answer is quite simple. Here's the rule. If the antenna is too short, what do you do to make it tune? You put a coil in it, right? A loading coil. If the antenna is too long, what do? You put a capacitor in. That's a loading capacitor. And the capacitor makes the antenna look electrically shorter. Simple rule. Your antenna is too short, put a coil in it. Antenna is too long, put a capacitor in it. They don't talk about this in most books, but this is exactly the facts that you have. So if we cut the antenna for 15 meters and electrically shorten it for 40 meters, well, we just insert a 330 puff capacitor at a low current point on 15 meters. And what's a low current point? Get to it. It's down in where the middle is. Those points there, a third of the way in. So you put the 330 puff capacitor a third of the way in. Guess what happens to 40 meters and 15? Okay, here it is. You can see it here. This shows you where to put the capacitor. You always put it at a low current point on the high band and a higher current point on the low band. And if you see what happens to the capacitor, there's the two SWR curves. One of them is without the capacitor, the other one is with the capacitor, and look what the capacitor did. It made it a perfect 40-meter antenna. Now, this is one of the experiments that Bob and I, by the way, when we write stuff up, we actually build everything and test it in my backyard. And this, by the way, was our COVID excuse to get out and do things. We did this all through COVID, and that's how we actually wrote this book based on that work. So here's what happens if you look at it for 15 and 40 meters. Now, these are all simulations, obviously, right, guys? And then if you build it, here's what it looks like. And here's what the real SWR curves came out to be. Would you run your rig on that without a tuner? Bet your life you would. And that's what it does for you. So the whole concept is you use capacitors to fix the problem that you have because multiples don't work and because end effects, I call it disappearing end effect. You get less and less end effect the more antennas, the higher the frequency, the more little loops you have, the fewer ends you have compared to the number of antennas. So things get worse. I call it disappearing end effect. Bob doesn't like that, so
that's all right.
We argue about it once in a while.
That's all right.
See if I can get this to go on. Oops.
You broke the symmetry of that dipole, didn't you?
Yes.
No, yeah, we did. Oops, come
So
on.
maybe it's not quite center driven anymore.
Oh, it
So
is.
the impedance may change a little.
Where are we here? We're going the wrong way. I'm going, where is it? This thing is slow. It's not going back. Come on. There it is. Okay. No, actually, it's symmetrical, but it's got that capacitor at 1/3 of the way in on 15 meters. That's all.
It's not symmetrical on 40 meters, but it is on 15.
Yeah. Anyway, so that's what it looks
It's a
like.
very small impedance change, so.
It turns out it just works, and that's the most important thing.
This was our first cut. We didn't tune it or anything. That's what we got.
Yeah, we actually did the calculations, we did the simulations, we built exactly to that, we put it up in the air, and we looked at each other and said, holy, 4-letter word. It was exactly what we had computed. That was very gratifying. All right, now, go ahead, Bob.
Okay, so going to an off-center fed antenna for a multiband antenna. When you move it off-center, you raise the impedance. And the question is, how far off-center do you want to go? A lot of antennas use 33% of the length. And that doesn't cover 15 meters very well. It's a very high SWR. So we use 20%, 1/5 of the length of the antenna. And that still is around 200 ohms. So a 4-to-1 balun will still work in that case. What it does do is it gives you more asymmetry. You're going to get more common mode current coming down the line, so you need much better isolation, really good 1-to-1 with lots of isolation. So, okay, so, okay, I covered that.
I think you covered it all.
Yep, okay. Okay, so
This is basically saying what we said before. If you're looking at optimizing the thing to work on all the bands, you have to decide that your basic length is going to satisfy the high bands first. Everybody else who makes an off-center fed satisfies the low band first. No, the low band you fix later. When you get the antenna cut so the high band's harmonics come pretty close, then it will work up there, and you have to fix the low band. And on 40 meters, we had to do that, and we used again the 330 puck capacitor at 30%, and everything worked well. The problem with this antenna, and this is one that we really discovered an issue, is that the antenna is so off-center fed that it's very unbalanced, and coax wants to grab the RF. It wants to come right back down into your shack. And it needs a very, very good 1-to-1. And we discovered that certain manufacturers' 1-to-1s aren't good enough for 40 meters, believe it or not, even though they're rated for 40 meters. So we designed our own, and we built one that has 30 dB of isolation on 40 meters, and the antenna works like a champ. We got several people using these right now all around the country.
So the 40 meter case is one of the easier cases because 40 meters is a narrow bandwidth band. You get to 80 meters and 160 meters, and that's a much higher percentage bandwidth. So that makes the problem much more difficult.
Well, this is the result of the 40 meter off-center fed. It's less than 3-to-1. It just makes it on 10 meters. And of course, who operates up at 29,700? We don't usually operate there very much, except repeaters.
Right, and they want vertical polarization.
Yeah.
So.
Okay, this is an 80 meter one.
Okay, this was actually first invented by a guy named Sergei Struband in Belgium, ON4AA. And
Bob's been corresponding with him quite a bit.
He's quite a character, actually. And he has a really good website. So you just, this has the 4-to-1 balun at 1/5 of the length of the antenna. The load is in the middle at it's 330 picofarads. And so we show the SWR curves here. So for 80 meters, it's just barely over 3.5, barely over 3 at 3.5. Everything else is pretty much below 3-to-1 except 17 meters. 17 meters is not harmonically related, so the non-harmonically related bands, you're sort of at the mercy of you get what you get.
If somebody tells you that they have an off-center fed antenna that works on all the bands, including the work bands, that means that they're using a tuner to make it work, because the work bands, you get what you get with those antennas. And we fiddled around a little bit trying to make them work, and sometimes you can catch it and sometimes you can't. By the way, this antenna is Bob's in his backyard. This is one of the first ones that was built.
So I have an ICOM 7300, and that can tune the 17 meter band. It's a little bit above 3.5, but it can still tune it.
Yeah, we built these things and we put Bob 7300 on all the antennas to make sure that it did actually tune it. This is a good one.
Okay, 160 meters. So if you go to Sergey's website, he'll tell you that the design doesn't scale to 160 meters, and we agree with that. The center load will fix 160 meters, but 80 and 40 will still be pretty far out. So we came up with a 2 capacitor solution. We put one at the current null for 40 meters, and that raises 40 meters, 80 meters, and 160 meters. And then we put another one at the 80 meter null point, and that raises 80 and 160. And it turned out that was enough for 160, and 160 was still in a pretty good place. So.
And this is my antenna.
Right. Yeah, so these are the curves we get here.
And notice 6 meters. It works on 6.
Yeah, we actually operated it on 2 meters as well, and it worked, but the repeaters didn't like the horizontal polarization. So we did a different one where we just kind of drooped the ends of the thing and made it shorter to hang up. And that, how much did we?
We took 10 feet droop down the end. It's a little longer because of the end effect is not as strong. So it's a little longer than what we would normally have if you just took the antenna and took 10 feet away. But it's actually in one of our articles on how to do it. And you droop the ends, and by God, it hit the repeaters.
Yeah, there's enough vertical stuff there that it worked reasonably well in 2 meters in repeater land.
So this thing works on up to 2 meters if you want to droop the ends. But, you know, that's just kind of for fun. You're better off just putting a 2 meter antenna up probably. But, you know, we did it just for grins. Now, what we learned about balance is a lot. We actually wrote an article about it, and it was in CQ in January 21. What we learned is that if you build a balance set for a center fed antenna, you use a 4-to-1, and then you use a 1-to-1 to isolate it. Otherwise, you're going to get RF down the feed line, and then you can put the feed line on the ground or hang it in the air. The SWR is going to go all over the place because the feed line becomes part of the antenna. By the way, one famous company who makes off-center fed antennas depend on that coming down the feed line. So you'll have RF in the shack. It happens with all of them. It may be more or less depending on how you do it. If you put a 1-to-1 at the entrance of the house, you may not have it in the shack. It'll just be in that wire. But they don't tell you that. If you want the thing to be horizontally polarized, you need to use a 4-to-1 followed by a 1-to-1 with a 30 dB isolation. And the problem you have is that some companies that make these things stack them one on top of the other. And guess what? There's enough mutual inductance that they cross-couple. And we discovered that if you cross-couple them, RF's coming back down. RF finds a way, and it's vicious stuff. Did you know that? And so what we learned is that if you put them at 90 degrees to each other, which is the one on the left, or you put them an inch apart, no coupling, and they work. So that's another little trick that we learned. We give it to everybody. And loads, go ahead, Bob.
Okay, so the capacitor loads, you have some requirements here. It's going to see a lot of voltage and it's going to see a lot of current. So you need capacitors that have a very large effective series resistance, equivalent series resistance.
Low series resistance.
Yeah, so we have these capacitors from Knowles and Cypher that are basically surface mount, but they're pretty big, so they're not too hard to work with. So we just take a little 1-inch piece of PC board and score a line down it to separate it into two sections and put the capacitors across those. And then you need a bleeder resistor so that the charge doesn't build up and reach a voltage that's damaging. And then you want to do something. You want to put this down on an insulator for strain relief, and you want to do something for weather protection. So what we do is we do a 3D printed insulator that has a little well for epoxy potting compound. And we have an epoxy potting compound that's highly insulative, it's conductive.
It's thermally conductive, which is
thermally
good.
conductive, yeah. So,
Anyhow, so that's our loads. Now, that's basically the off-center fed stuff. Now let's go on to the next one. NFED. Anybody here have an NFED? Does it work well on all bands? Okay, we'll show you how to make it work well on all bands, including the ARRL NFED that they sell. Doesn't work well on all bands. But we'll show you how to take that antenna and make it work well on all bands. Okay, NFED transformers. This was my project. Spent a lot of time on this. The one on the left is a conventional one. What they do is they wrap two wires together, and you can see it on the, probably let me just do this. You can see it right here, that the wires are wrapped around. There's two turns, which is the primary of the transformer, wrapped around the end of the secondary. Now, what's the purpose of the transformer? It's to take a low impedance and make it into a very high impedance. And what happens if you put high impedance and wrap wire around it? You've made a capacitor. And you're basically shorting out the damn transformer. And that's how they make them all right now. I looked at that and I said, why are we doing that? That doesn't make any sense.
And they get real hot too.
They will get hot. And there's a whole thing about heating in NFEDs. And we did a whole study of that. And we actually put thermally conducted tapes on the box, put it up in the air, and put 500 watts in it to test them out. And we found that the way we were doing it, the temperature rises were quite comfortable. But yes, you got to be careful with that. And that's also in our articles. The solution is simple. You don't put the primary on top of the secondary. The middle of the transformer is a low impedance point. So you put it at the low impedance point. What the transformer wants to see is the current from the primary. That's all. So you put it in a spot where it doesn't affect anything else. When you do that, the bandwidth of the transformer goes up. When you build them the way they're building them now, it's a low-pass filter on your transformer. That's silly. So that's what we do. So now, it turns out that Ballon Designs discovered this, and they called me up. And they now make an 800-watt 36-to-1 transformer, which is the ratio that we use. And by the way, 36-to-1 is because the impedance of the antenna is less reactive at 36-to-1 than it is to 49-to-1 or the other ranges that they use. 36-to-1 is the optimum. And there's several articles about that. We proved that that's the case. But anyway, the conventional transformer uses a 100-puff capacitor to tune it basically, and we use 56 puffs because we have less loading. So the transformer really works quite well. Now the one that's in this picture is a low power one. It will handle 100 watts, and it works on any antenna that we show you NFED, from the lowest frequency that the wire's cut for to 6 meters. They work all the way up to 6. Try to take one of the commercial ones and put it on 6 meters. You'll get nothing. You won't hear anything, and it'll load up 1-to-1. That's because it's all lost in that transformer. Okay, let's go on.
Okay, so what we discovered, well, I guess we found this online in references. If you use a counterpoise that's 5% of the wavelength of the lowest frequency band, and you use a 36-to-1 transformer, then the point where the resonance occurs will be pretty close to the point where it's 50 ohms, which is going to give you the lowest SWR. So that's sort of a magic ratio there. So we have our 36-to-1 transformer. We have 13 feet 2 inches of coax, and then we have a 1-to-1, and that gives us our counterpoise.
Now recognize that we also tie the one side of the transformer to the coax. And that's the and therefore the shield of the coax becomes the counterpoise. And when you put the 1-to-1 13 feet below it, you know how much RF I've got in my shack? This is my antenna. 0.
So anyway, so then we use the same trick with the capacitor to make the bands line up. And in this case, we used 150 picofarad capacitor, and it's at about 32% of the length.
Right.
And we can do an 80 meter one like this. We can do a 40 meter one with the same components, just different wire lengths.
And we'll show you the numbers for that. But I want to make another point that I slipped in here on Bob. You want to control where the RF is going off that transformer. You can read all the manuals, and they say, oh, we don't need any counterpoise, just ground it at the shack. Bullshit. Because it will come into your shack if you don't have the right length of wire on it. It depends on the length of the wire, and the resonant frequencies, especially on 10 meters, depend on the length of the counterpoise. And Bob did a whole bunch of studies of this and proved that the 5% on a counterpoise, on our 80 meter antenna, gives us low SWR at the top of the 10 meter band. And without it, it's whatever you get. So you want to control where the RF goes. Don't depend on being lucky. Okay.
These are the SWRs we got. And I was not actually too enamored with the idea of an end fed when we first started this. I thought the off-center feds would be better, but these are lower SWRs than we get with our off-center fed. So, and it's nice. It's easy to string up. It's easy to take down. It's great for field day.
Yeah, it's a good antenna. I use this. This is my go-to antenna now. I have the off-center fed on one side of the house. I have the end fed on the other side. I have the dipole somewhere else. I got a lot of antennas. We have to have a place to test antennas, so I got ropes all over the trees. My wife calls it macrame trees. But you'll notice that, look what it does on 12 meters. And that's what you get. You get what you get, but that's what you get. It's pretty damn good. And this is a 40 meter one.
Okay, again, it's the same components, 150 picofarad load, and the 36-to-1 transformer, and the same 1-to-1, but the length of the wires is different, and the length of the coax for the counterpoise is different.
Notice this one on 6 meters looks pretty good too. This is the one we've been using on field day for our motor station. It's easy to put up. We put it up at the end of it, maybe 15 feet, the driven end, and then the other end goes up as a sloper to about 40 to 45 feet, and we get out like crazy with it. It works great.
We also use the 80 meter one for the CW station.
Right. And we use an off-center fed for the sideband station. Okay, we're going to change the subject. Phase dipole wire beams. This is one of our most fun projects that we've ever done, and probably the most complicated. And a conventional Yagi uses multiple elements of different sizes. This is the driven element in the middle. This is a director, and this is the reflector. The reflector keeps stuff from going this way, and the director makes it go this way. Phase dipoles are different. We have 2 dipoles, and we drive both of them. But we phase the signal going to them so that it forces radiation in the forward direction. And this has been the most fun project we've ever done. Bob, you want to talk about
Okay,
this?
so this shows the 2 driving waveforms, and it's maybe a little hard to see, but they are out of phase by 90 degrees. So that means that the wavefront going from dipole 1 to dipole 2 will arrive
90 degrees.
90 degrees, yeah.
And then here's what happens.
Right, so they arrive coherently, and so they add up. And if you go in the opposite direction, they're out of phase.
That's the next slide.
And they cancel. So you get forward radiation and pretty good front to back.
Now this is 90 degrees, which is what every book shows you, 90 degree separation. We had a problem. Our goal was to build something that we could move in our van. And 25 feet of spreaders is too much for spreaders. So we said 10 feet. That's all we can put in the car. So we got dowels and lows. And 10-foot dowels, and we started to design towards that. Well, Bob, there's a problem with that. You discovered it.
Okay, so the quarter wavelength is actually 16.3 feet, so that would be the length we should be using. And when we use 10 feet, then we only have 52 degrees instead of 90 degrees. So what we can do is we can change the phasing delay line to make up the difference for cancellation in the reverse direction. And when we do that, then we get a really good front to back. We lose a little bit in the forward direction, but it actually forms a fairly narrow beam, and the gain is based on the directivity of the antenna. So the narrow beam gives us about 11 dBi of gain.
This is now a 2-element beam with 11 dBi of gain. Can you believe it? We couldn't either when we started looking at the numbers. But the idea of, instead of trying to optimize forward direction, we're going to minimize rear direction. So if you think about radiation from a point source, which you often see, which is a sphere, when you put it to the ground, the sphere tends to change its shape a little bit. But if you take that sphere and squeeze the back of it, and that will force the radiation the other way, and that's exactly what this does. It's like taking a balloon and squeezing one side of it, which is the back side of the antenna, saying, no, we don't want any air in here. We want the air all over there, and that's what happens. And the results are absolutely great fun.
So we have a phasing line that generates the phase shift between the two driven elements. And so we adjusted the length of that to give us 180 degrees given the spacing we had. And so that gave us cancellation in the rear direction, and we still get good forward gain. So that's what the antenna looks like. So we have these spreaders. Let's see. Here's my microphone. Okay, so these are the spreaders here. And then these are the two elements here, 16 feet for each leg. And these should be identical. And then this is a rope that goes down the center of the spreaders. And we have a box that has the phasing line, all the other stuff we need, and that hangs right in the middle. And so this rope, the support rope, prevents the weight from pulling the two antennas closer together. And then we hang it up with a harness. And this is what's inside the box. This is what's inside the box. So there's a connector here for the two dipoles. This is the phasing line. And this is where the graph comes up. We have a latching relay, single coil latching relay. And we can either drive this side directly and that side to the phasing coil, or we can drive this side directly and that side to the phasing coil. So now when we do that,
that flips the direction 180 degrees.
So when we do that, then the impedance that you see here is actually only about 8 ohms. And the two elements interact, and you get a very low impedance.
It's 9 plus J9 on the 20 meter one.
Okay, yeah, we scaled this for 17, 15, 12, and 10 meters. We got
and 6.
We got slightly different impedances. But anyway, so this is that matching network, which is a pi network. And this is the one-to-one choke. And then we had a bias T circuit for sending the control signal for the relay. So we have to strip the control signal off to drive the relay. And that's it. Okay.
Now here's what happens. We put it up in the backyard. We go out with my KX3 on a battery, and we put it on the air. And the first time we put it on the air, we didn't know which direction it was set for, and it turns out it was set to Europe. And my backyard is a pretty good shot at Europe, the way the trees are. And we worked about 5 or 6 European stations with decent reports on sideband with 5 watts. So then what we did is we finally got the bias T working and the relay working, then we can flip it. So we put it up again, and we were working Europe, and then we couldn't hear any US stations. So we flipped it to the US stations. We couldn't hear any European stations. Wow, we said that's pretty cool front to back. Our modeling said we should have around 12 dB front to back. Well, we weren't getting 12 dB front to back. We're getting more. And so we did a bunch of measurements with in our club. This is a park club at Westbrook we belong to. And we got measurements between 2 and 5 S units front to back ratio. And we got the same thing when we were dealing with some stations that we were talking to. So this is an antenna that has 11 dBi forward gain and front to back ratio averaging 3 S units. Unbelievable, and it works great. So then, we used it field day last year, and we're in a building that tests at the Concord Rod and Gun Club down here in Concord, Mass. And they put something in that building that generated more racket on 20 meters on all the antennas, including this one, until we switched it to aim. The antenna was on the west side of the building. Thank God it was there, because when we flipped from east to west, the noise disappeared and the signals came up. The 5 S unit front to back paid off for that spot. There was so much noise on the other antennas that we had on 20 meters. We had the end fed up. The noise was from the building was just unbelievable. So we got rid of the noise. So anyhow, so it's a fun antenna.
Okay, so I guess this is the sum up here. We're pretty much done. So the capacitive loads allow you to line up the bands for multi-band antennas, so you can get a low SWR on every band. Excuse me. We've got the phase dipoles for 20, 17, 15, 12, and 10 meters. We tried to scale it for 6, and it didn't work well for 6. So we had to come
That's
up.
why I have thin hair.
So we had to come up with a different design for 6. But we did that, and yeah, we built everything and we tested. And we use these things ourselves. Our club uses pretty much all of these antennas for field day.
We have a whole box of antennas for field day. We just sorted them out from last year's, throwing them in a box. So we're ready for field day. Anyhow, we've written a book called Wire Antennas from 160 to 70 centimeters. And we took all the work that we have been doing for the last 4 years and kind of compiled it into the book. And then we added some things that we hadn't done that's not been published before. The book is available on our website, which is ocfmasters.com. We got a couple of copies here if you want to thumb through them just to see what they look like. And we had a lot of fun doing this. And our whole goal in writing the book and doing the articles and making the antennas was not to make any money. We wanted to give it to everybody, every hand, so you can do the same thing and make better antennas. That's our goal. And that's it. Thank you very much.